So my name's Daniel Situnayake. Nice to meet you if I haven't seen you before. And if I have, thanks for tuning in again. So we'd like to, first of all, thank our tinyML Talks sponsors. So first up, there's Edge Impulse, which I'm a big fan of. You can see is the company I work for. We then have Maxim Integrated and Sincents, and we have messages from some of those sponsors later on. So if you're interested in sponsoring tinyML Talks, we'd be really excited to hear from you. And you can contact Betty at tinyml.org for info. So our next tinyML talk is coming up on Tuesday, June 23rd. We have these every Tuesday, pretty much every Tuesday. And our first presenter is Yung-Hsiang from LG Electronics America Research Lab, talking about a weight averaging approach to speeding up model training on resource-constrained devices. And our second talk is from Brandon Rumberg at Aspinity, talking about analog ML and how analog ML is relevant because most sensor content isn't. So that's going to be same time next week. And if you are interested in presenting at a future talk, just let us know via talks@tinyml.org. So first up, we have Low Power Computer Vision by Professor Yung-Hsiang Lu from Purdue University. So Yung-Hsiang Lu is a professor at the School of Electrical and Computer Engineering and courtesy at the Department of Computer Science of Purdue University, West Lafayette, Indiana. Dr. Lu's research topics include energy efficient computing, computer vision, mobile and cloud computing. He's ACM Distinguished Scientist and ACM Distinguished Speaker. He's the lead organizer of the IEEE International Low Power Computer Vision Challenge. Dr. Lu is the inaugural director of Purdue's John Martinson Entrepreneurship. Students from his research team started 2 technology companies using computer vision for retail stores and raised more than 1.3 million small business innovation research grants. In 2019, he received the Outstanding Entrepreneurship Award from the Vertically Integrated Projects Consortium. Dr. Lu obtained his PhD from the Department of Electrical Engineering of Stanford University, California, USA. So now I'll hand it over to you.
Thank you. Thank you. Good morning. It's my pleasure to have an opportunity to speak here and share with you some of my recent work, as well as some of the progress made by the whole community. So today I will talk about low power computer vision. And this presentation actually includes 3 parts. First, I will give a bit survey of some recent work on low power computer vision. Then I will share with you some of the progress made by my research team. Then I will talk about the low power computer vision competition. You can find a lot of information on the website lowpowercv.ai, and also if you want to join the Slack channel, there's a lot of discussion there. As I checked yesterday, there are already more than 150 people and more than 1,300 messages posted there. Computer vision in general is kind of energy hungry for many reasons. One reason is computer vision needs a lot of data as input. An image can have millions of pixels, and for video, if you add the time, that the data can be gigabyte of data easily. At the same time, digital cameras become very cheap, and it's very easy to produce a lot of data. So, I'm sorry, I clicked the wrong button. So the most commonly used method for computer vision is neural network. These networks usually are very deep, means they have many layers, and each layer has many neurons and many parameters. So everything together, it's just a lot of data, a lot of parameters, and they usually don't fit into cache. There will be a lot of memory access. That means even more energy consumption. So that computer vision in general is very energy consuming. And I'm sure many of you have seen this picture from NVIDIA. Last month, NVIDIA announced their recent product, and it's so hot you had to put into your oven. So why do people care about low power computer vision? There are many, many reasons. First, digital cameras are cheap and they can be everywhere. Your phone has probably 2 cameras or more. one on each side. If when you take a photo of some event, let's say you go to a birthday party, you may want the computer vision to know automatically whose birthday is that. If you go to a concert and take a video, you may want to know who are the players and the musicians and so on. You go to a sport event and take a picture or take a video. Do you want to have a computer vision automatically figure out who scores? Right? These are some examples of the applications of computer vision. If you go to a famous restaurant, maybe you want to take a picture of their dishes and you want the computer vision to tell you what the material, what the ingredients are used in a dish. We can imagine to put cameras on embedded systems for many other applications, such as safety. You can imagine a factory want to use computer vision to detect whether everybody is wearing protection, such as hard hat. Now because of COVID-19, maybe you want to put attach a camera outside your door to see whether everybody is wearing a mask. Right? These are many examples. And you want to use batteries for most of the applications I mentioned above because you don't want to have wires or and so on. It's getting very inconvenient. This shows on the right side of the slide shows health care robots. You want a robot to take care of a patient. You don't want to spend most of the time recharging the batteries. You can buy a camera and put on a tree to observe animals. As it is now, the technology can take pictures, but it does not analyze which animal you have observed. Right? Is it a deer or is it something else? Of course, you can put the surveillance cameras in places where grid power is difficult to get. And you can, if your computer vision is low power, then you don't need to connect to the grid. Drone obviously has cameras, and we want to have computer vision running on board to know what is seeing, and maybe eventually have autonomous navigation. An application scenario is, let's say after a disaster, you launch several hundred of drones, you want to know how many people are waiting for rescue, and you want to have some kind of communication among the drones to figure out how much resources you need. In this presentation, I will cover 3 topics. I will give a survey of some methods for low power computer vision. Then the second topic is the recent progress of a hierarchical neural network for low power computer vision done by my research team. And the third is the computer vision challenge for this year. You can find more information at the bottom of the slides. So as I discussed with Daniel yesterday, I will give people a bit time to jump in and ask questions. So is there any questions so far?
So we don't have any questions in the Q&A system yet, but if you do have a question, please add it. And next time we have a break in the talk, or if there's something especially pertinent, I'll be able to read it out. So feel free to add your questions there in the Q&A tool. All right, thank you.
So in this quick survey, I will talk about computer vision, low power computer vision, break them into 4 categories. The first category is to quantize parameters and prune connections. The second is to compress filters and factorize matrices. The third method was search for efficient architecture. And then the fourth method was distill knowledge. Quantization is one of the most widely used methods for reducing energy consumption in computer vision. In general, when people train neural networks, they usually start with 64-bit double precision floating point numbers. But in many cases, we don't really need so many bits to encode the numbers for weight and bias and so on. So many studies have shown that it is not necessary to use double precision. Instead, people use single precision 32 bits floating point numbers. And some people use even lower precision or fixed point or integers. In some cases, people even use just 1 bit to represent the numbers, either 1 or 0. In general, when you have a higher precision, you can have higher accuracy, but at the same time, you need more memory and you need more energy consumption. Therefore, precision is a trade-off between the amount of memory and the accuracy. Another commonly used method is proving network connections. You can see in this figure, on the left side is fully connected between layers, and on the right side, you can see some connections are removed. Sometimes after training a neural network, we realize that the connection between two neurons are not very strong, meaning the weight is very small. Therefore, we just remove that connection, and that can reduce the size of the network. Only some of the neurons are connected. Network proving is often get connected with, used together with parameter quantization, but the training time usually takes longer. The reason is you usually will start by training the fully connected neural networks, then you realize which weight is too small, then you remove the connections. But you have to make sure that does not hurt your accuracy. So you have to validate your accuracy again. So that training process usually takes longer. This table shows some examples of neural network proving and quantization method. Here we consider two data sets, the MNIST and ImageNet. As you can see, the amount of memory can be reduced quite dramatically, but at the same time, the error rate almost unchanged, so that's very good. The next method is to compress filters and factorize metrics. This slide shows a very simple example. Consider a 3x3 kernel. You can decompose this into two kernels. The original filter needs 9 parameters, and the new approach needs only 6 parameters. Therefore, you can reduce the memory requirement. This slide shows an example using the ImageNet dataset. DenseNet uses 32 megabyte memory and has more than 3 billion operations per image. MobileNet compress the filter and factorize metrics, needs only 2.5 megabyte memory and has only 2 million operations. However, MobileNet sees drops in accuracy. This method has two limitations. First, it's effective only for large neural networks. In the early example, a very simple example we saw, you only reduce from 9 to 6. That's not a huge amount of reduction. So it's effective only when your neural network is already large. And second, it does not use GPU very efficiently because when you factorize neural network, you have a more memory access, your data reuse becomes less. Therefore, you actually have to pay more memory access for this method. The third approach is get very popular in recent years. It's called the network architecture search. In fact, you can see in many publications, it's simply say NAS, network architecture search. This method can be described using this picture. There is a control and it adjusts the hyperparameter for the network architecture, such as the number of layers, the number of neurons in each layer, and so on. Then the controller will train the network using this architecture, then evaluate the performance. This process can iterate many times to find smaller network and that can still obtain the desirable level of accuracy. This method is usually used to optimize specific hardware device or applications. Imagine you have different kinds of phones or with different characteristics, different amount of memory, different processors. This method can be used to optimize for different architectures. This method has drawbacks because in order to do this, you often need to consider many options. Basically, this method will adjust the network architecture, train, evaluate, and iterate this process through many options. If you go to MIT Technology Review, an article published about a year ago, it says this training process can emit as much carbon as the lifetime of 5 cars. So there's some recent work by MIT, Professor Han Song, talk about how to improve this training process to make it much more efficient. Another method is called network distillation. This method is actually using two neural networks. One is a larger neural network and already trained neural network. And then another one is a smaller untrained neural network. They play like a teacher-student kind of relationship. The training data will pass through the two networks. The loss from both the large trained network and the smaller untrained network is used for backpropagation. So the concept is the following. As you pass the data through the networks, if there's an error, then you can add the error together to amplify the error and then use that error to backpropagate to train the smaller neural network. This process has been shown to accelerate the training process. So that is the first part of my speech, a very quick survey of recent work on low power computer vision. I'm going to pause here and see whether there's any questions or for discussion.
Hey, thank you. So we have a couple of questions. So one question from Kartik Akela was, why is the matrix factorization approach only applicable to large networks?
Oh, because it's not only applicable, it's more effective for large network. There's very small example shows that if your original matrix is small and you do factorization, the amount improvement is very small. It's not applicable. It's applicable, just you don't see much of the advantage.
Okay, perfect. Thank you. And so I had a couple of questions. So for these models across the board, were they broadly benchmarked using the same data set? And which data set is that if people are doing their own experiments?
Okay, very good question. What data set? The answer is there's a wide range of data set. I think I showed several. Depends on the applications. Some of them have small data set, some have very large data set. I think it depends on the purpose. For example, if you want to recognize handwritten numbers, you don't need ImageNet. ImageNet is more for photo. So you probably use the MNIST data set. So depends on the application, you want to choose the proper data set for training and evaluation.
Okay, fantastic. And last question. Oh, here we go. So we've got a few more questions. In fact, a lot more questions in the QA now. So let me sift through. So question from Sergio. Is there a benchmark for defining what low power is today for computer vision use cases?
Yes and no. Usually people use joule per image. That's pretty widely accepted. But that, again, that's not it depends on applications, right? If you want to classify image into 1,000 different kind of animals, let's say, versus you want to classify 10-digit handwritten digit for your mail, so you have to look at the applications. There's no single, I don't think there's a single way to measure it. Some of them, usually the metrics include the amount of memory, the time, you can say millisecond per image or millisecond per frame of a video, joule per image or joule per frame of video, and so on. There are a wide variety of metrics. One of the things we hope to do in my third part of the speech is we want to have an open competition. We will tell people everything except the test data. So we will tell you exactly what kind of hardware we use, exactly how we measure everything, with the hope that the people will use at least the same metrics for comparison if they are designing for the same applications.
Hey, fantastic. So Josh had a question, which is, can you speak to the number of flops reduction that is produced from each of these techniques you've outlined?
Not really, because first, flop is not always the best way to measure things. Second, I don't have enough time to talk here. I guess we have to discuss that offline.
Cool. And so to that point, if we have any questions remaining at the end, they'll be given to the presenters who can answer them in their own time, and we'll post those on the forum.
Sure.
So I think it's probably good to move on to the next section
Sure.
now. Thank you very much, everyone.
Yeah, I have my email address here. I will be more than welcome to have a further discussion. For the interest of time, I promised John I'm not going to take away his time, so I'm going to speed up a little bit. The second part is the recent research in my research team. We look at how we can reduce the energy consumption for image recognition. This picture shows a very simple concept. We call it hierarchical neural network. At the top of the slide, you can see how people usually do for classifying images into different categories. In this simple example, we consider truck, car, cat, and dog. The traditional method uses one large neural network to classify all categories. In the lower part of this slide, we use a small network to do the initial processing to classify them into vehicle or animal. Then we use another 2 different neural networks to further distinguish them. And by doing this, we have discovered that each neural network can be much smaller than this originally big neural network that can do everything all together. But there are many challenges. First, we have to decide how to group them. In the earlier example, I used car and the truck and dog and cat as 2 different groups. But we have to consider what do we actually do when we want to group the data. We consider several methods. One method is called visual similarity. Another method is called semantic similarity. For visual similarity, we will put birds and airplanes together because they are in the sky. If you see they have wings, even though they don't really, they are quite different in terms of semantics. Birds are animals and the airplanes are machines. In contrast, if we consider semantic similarity, we will say banana and apple belong to the same category because they are fruit. However, they are visually dissimilar. You can see banana is kind of long shape and the apple is kind of round shape. We also need to consider how to use small neural network as small as possible. So the method we use is to start with as simple as possible, and we gradually grow the neural network until we hit diminishing return. When we further grow neural network, we don't see much improvement in accuracy, then we stop and use the smallest neural network we have discovered. And the third method is we need to know how to train a neural network. Now we have a many neural network, we need to train all of them together. This slide shows the concept of how the neural network are put together. The output of the parent network, it becomes an input of the child. By doing this, we can reuse the computation we have already done in earlier layers. That way, we don't have to waste computation again. So basically, we are not passing the image down the tree. We are passing the image into the root only. And then from there, we pass the output of the parent node to the child node. This figure shows the tree we built for CIFAR-10 dataset. As you can see, we do not restrict the number of children for each node. A node can have 2 or 3 or 4 children. The width and height is a trade-off. We don't want it to be too wide. If it's too wide, it means too many children. That means it basically go back to the original big neural network. But if we don't want it to be too tall, if it's too tall, then it will take much longer to process each image. There's more detail in the paper. We have compared our method with many other methods, and we see our method has much less memory and also lower energy consumption compared to existing methods. We are finalizing our paper. They have been accepted. We will release the source code, and so anybody interested will be able to see how we do it. For the interest of time, I'm going to, Daniel, how about I finish the third part and then we can open for questions? Does that work? Okay.
Yeah, sounds perfect.
So the third part is the low power computer vision challenge. We had a workshop held yesterday as the part of a CVPR workshop. And we have recorded the speech. So if you go to LPC Vida AI, we will upload the speech very soon. The challenges online will be held in July. There's no travel, so everything is online. People can submit their solutions online. This is actually the 6th year of the competition between 2015 and 2019. We had only image recognition. And in this year, we add video, so rename it as Low Power Computer Vision Challenge. Again, please join the Slack channel for discussion. This slide shows the 3 tracks we have for this year. The first track is video captured by UAV and using PyTorch. The second and third track are image for using FPGA and the TensorFlow. Again, all information is on the LPC.ai website. If you are interested, or you know anybody interested, please encourage them to visit the website. For the interest of time, I will skip the next few slides. Basically shows the history. And since 2015, we have quite a few sponsors and appreciate all their support. The participants all actually come from all over the world. The winners come from China, Korea, Canada, Russia, USA, and so on. We have the winners come from both academia and industry, Qualcomm, Amazon, and AppleSoft. Not the Apple is AppleSoft from Russia. They have won the competition before. To summarize, low power computer vision is a very active research area, and there are lots of papers published. We have a survey paper going to be published this year in IEEE World Forum of IoT. And our recent work shows that hierarchical neural network can save energy. And finally, I encourage you to participate in the 2020 Low Power Computer Vision Challenge, or encourage your collaborators to participate. If you are interested in further discussion, this is my email. And the last 2 pages are references. If you are interested in getting the slide, I think you can either ask tinyML or you can contact me. Thank you.
Thank you very much, Yung-Hsiang. That was fantastic. And we do have a few questions, but I think probably more than what we have time for. So I'll just ask one question. So regarding knowledge distillation, this is generally a little bit more complex than some of the other techniques. Are you aware of any examples of knowledge distillation that people can easily follow if they're doing their own research?
I don't know easily, but there are some papers. So if you go to our survey paper, there you can find some papers there.
Cool, thank you very much. And so for the rest of the questions, in the interest of time, I will relay those to you after the talk, and we can post the answers on the forum.
Sounds great, thank you.
So thanks again to our tinyML talk sponsors. So those are Edge Impulse, Maxim Integrated, and Sincents. If you're interested in sponsoring this talk series, please contact Betty at tinyml.org for information. Thank you also to Zoom for slowing down my slide advance. Okay, so a little bit of information about some of our sponsors. So Edge Impulse, I'm a little biased, but I think we're the easiest way to train a model for inference at the edge, and in fact, probably in general. We have an awesome interface you can use to connect an embedded device, collect data, train a model, evaluate your model, and deploy it back down to a bunch of different targets using the optimizations that are available for each target. So you should definitely check out Edge Impulse if you'd like to rapidly train models and deploy to edge devices. And our sponsor, Sincents, formerly known as AI-CTX, builds ultra-low power, sub-milliwatt sensing and inference hardware for embedded, mobile, and edge devices. So they design systems for real-time, always-on smart sensing for audio, vision, biosignals, and more. And you can learn more about Sincents at aictx.ai. So our next talk, as I mentioned earlier, from Unmesh Kurup at LG Electronics America, is a weight averaging approach to speeding up model training on resource constrained devices. And our subsequent talk from Brandon Rumberg, which is analog ML is relevant because most sensor content isn't. So that's on Tuesday, June 23rd, next Tuesday at 8 a.m. Pacific, same time as this one. So please come along. And you can contact talks@tinyml.org if you would like to present yourself. So I just wanted to thank everybody again for attending. Thank you. Huge thanks to our two excellent speakers today. And thanks to the whole tinyml.org crew for organizing another successful talk. Looking forward to the next one.